Guys, it's AxiomaticUncertainty here, and I'm back with another video, and I apologize for the time between videos, but also for how quiet I'm being in this video, just because, I'm not really sure how quiet I'm being specifically, but I do know I'm trying to keep my voice down a little just because, there are other tenants here, and I'm not trying to be too disturbing to those people since it's a little bit late at night. But for today's video, I'm just going to be going over an update to the Spline video that I made. I know probably people are expecting something for the car tutorials, and I think as this semester starts to wind down, I'm going to try to maybe get back into uploading some YouTube content. Right now I'm in 19 credit hours worth of classes, so it's a little bit much for me to really want to upload this kind of stuff. At the end of the day, I kind of just want to relax a little bit, so that's kind of tough, but afterwards I think I'll try to get back into that. So in the meantime, this is what I'm uploading. I made this a while ago, but I never really updated anybody on it, so I figured I would owe that to you guys. And so what this is this is a roller coaster simulator kind of thing. It's very basic, really bare bones, but this was just a proof of concept for what I was going for with the splines initially. This was the reason for which I wanted to make them in the first place. So you can see here there's a chain lift that this ball is kind of going up, and what happens basically when it reaches the top is that we enter a physics simulation where you can see it drops down and it simulates physics, and as it's coming up you can see it's applying gravity, and then when it hits here, it hits a brake line actually where it starts to really decelerate, and then it comes around into this final turn and up here, and you can see there's some problems with skipping, and I'll get into why that happens and some potential solutions in a second. But yeah, that's what we have for today that I wanted to kind of show you guys. This is the spline that it's rendering, and you can see these are the breakpoints on the spline. As with before, the scale of the spline is what determines the size, right? So you can see if I scale this up, in theory, this spline size should change, though I think I actually changed the way in which this works. Yeah, I did. Actually, I'll explain that as well since I forgot. But yeah. So you can see in here there are a couple things here. I have 3 classes open, and the first class is the one that was in here before, which is the spline class. We'll get to that in a second, but we also have this vertex class, and you can see I replaced the initial spline class scaling aspect, which I think was not in the last video, with magnitude forward and magnitude backward. This allows you to change each individually instead of just having one value for both. So basically like a vertex in Photoshop or anything like that. Yeah, so basically the way this all works is we have a spline that has a list of vertices, right? So in here you will see you can assign these vertices, right? And they're all dropped in there. And then we have, types of track for each of them. You assign those in here. Basically, the word that you put in the track is what determines that. You can see here, this track and this track, these are lifts, meaning that they will pull the car across from here to here and up. And then this is normal track, meaning it just simulates physics normally on it. And these are brake tracks, meaning that it will decelerate the car as it goes over them, and I believe that's this track point here. Okay, so now that we've gone over just sort of that stuff, you can see we have the track type list, the renderer prefab. That's all from the previous section except for this track type bit that I mentioned. And then we have the same kind of structure for the spline, except if I remember correctly, we didn't have this list property. What this does is it lets you create a series of instances of this piecewise cubic object, and these can be assembled into this list of pieces. And then we have this prev_r game object, and we'll get to all this stuff. So in here, at the start of each frame, we clear pieces, right? And then what we're going to do is we're going to update the pieces. So you can see we go in here to the vertices, and we just add new pieces. And the way this works is we create a piece with the position of that vertex, the position of the next vertex, the transform, right, for the up of that vertex, which determines the angle of the track coming out of it, right? The spline angle is determined by the upward transform on that side. And we multiply that by the magnitude forward component, which, as I mentioned, is here. And that determines the basically the derivative at that point. It's not the, it's the all the partial derivatives. So it's the nabla, I guess, is the name. I can't remember the actual name other than nabla, frankly, but if anybody's taken multivariable calculus, maybe you can step up and explain, because I cannot remember the actual term other than that. But yeah, so here we have, again, the next vertex multiplied by its backward magnitude, right, because that one is pointing in the other direction. And we create a piece. And when we do that, you can see this is a new instance, right? So you'll see what happens when we pass it, which is we have A, B, C, and D, right? So these are just the parameters, the coefficients for the general form of the cubic equation, right? Which is ax cubed plus bx squared plus cx plus d. Then we have a length value, which is the length of this particular spline. And then we have the actual constructor method, which I just mentioned. So what this does is we get the values that are passed in, right? So the first one being the location of the first point, the second one being the location of the second point, the partial derivatives at the first point, and the partial derivatives at the second point. And we basically plug them into, or we basically just plug these into formulas, right? I cannot remember if I derived these formulas, or if I found an example derivation online somewhere. I would assume it's the latter, but you know, if not, I'm not really sure. I'm sure this has been worked out better. If I came up with it, I probably did a pretty poor job. So I can try to find a resource on this, maybe, if somebody wants to know more about this. But basically, you're just taking the partial derivatives and these values and, you know, trying to set them all equal and solve for these individual values, which is probably just some simple linear algebra. Okay, so now that we've gotten that out of the way, you solve for all this stuff, and now that you have all of these values, all you need to do is use these in the future to calculate certain things. So for example, here we have a calculate point value. What this does is, right, these are parametric equations. We can pass in a parameter t and calculate the point that corresponds to t on this cubic spline, right? And that'll return the vector for that location. That's pretty simple, I think. I would say this is pretty straightforward, hopefully. And then we can calculate the delta as well, right? So, oh, and I think I forgot to mention that these are actually vector 3s, because obviously we have 3 dimensions to this spline, right? It's basically 3 cubic equations all being combined into this amalgam that forms the spline. Sorry, this is a bit much, I think, in terms of content, but, you know, I'm trying to sort of get through it in a way that's digestible, since, as far as I know, I don't think I've seen any really good information on splines in Unity, which is a part of why I decided to make this in the first place all those months ago. Yeah, so we calculate delta as well. What calculating delta does is it basically just returns the, again, nabla. I can't remember the term for that. Let me actually look that up really quickly. I don't know. I just can't remember the actual name. Because I just called it Oh, okay. I'm so dumb. I'm sorry. It's good gradient. I don't know why I forgot that, but yeah. Whoops. Yeah, so this basically just is, really simple. You just take the partial derivatives with respect to each value, right? Really easy to derive. This is just power rule applied to each of the three parts of the vector. And then we plug in the parameter and calculate the gradient at that location on the spline. And then get type just gives the type of track at that location. Though I don't think that this is particularly necessary, but either way, we also have a set type method. And these are just get set type things so that we don't have to directly interface. Okay. Get points. So let's see. This one gives you render points just for rendering. I think I mentioned that in the previous one. Again, this one's just a generalization of this calculate point vector 3 thing for the individual. This is for the piecewise cubic, right? So when we combine all of the cubics into one giant spline, right? We get this get spline position, and what this does is it goes through each of the pieces, right? And basically, I mentioned this earlier, but we have a length parameter for this, but we also have a length for the entire spline. And so if I remember correctly, the way in which we actually do this is we go through, right? So you can see we go through each of these, and we set x to be equal to the clamp of t between 0 and 1, right? Because t is a parameter for the spline, and so 1 should be at the end of the spline, 0 should be the beginning. And we just go through and multiply this by the number of pieces, so that basically what we can do is we can use the actual integer value to determine the piece index, and then we can use the other component of it, which is the non-integer component, right? You can see we're indexing using the truncated version of x, right? And then here what we're doing is we're removing the truncated version of x from x to get the decimal component, and then we're using that instead as the parameter value. Now, I would say get spline position like this, pretty bad idea if you're just trying to outright get values like this, because what this means is that if you have splines of different lengths, this is going to be super inconsistent about how it behaves, right? Because this is not normalized with respect to arc length, which I will get to in a second. So there's no normalization going on here of any kind. Okay, so get spline delta, basically the same. We're not really going to need to go over this, right? We just perform the same computation, but instead of getting the point, we get the gradient at that location. And calculate length. So this is where it starts to get a little bit more important for the roller coaster simulation aspect. And I'm trying to sort of move through this a little faster because, again, this is a ton of content that we're going through here, and a ton of work that you would have to go through. I think it's a little bit of an intellectual exercise, which is why it's such an entertaining thing to try to work on. But yeah, so you've got this function that calculates length and the number of steps for this. So what that means is we're going to divide the parameter t, right, over a certain number of steps. So like say we specify 10,000 steps, we will, perform 10,000 iterations over the spline and check each of those locations, right? So 0, 0.00001, et cetera, et cetera. 1,000 times, so, or 10,000 times, so precision to the 10,000th place. So yeah, we take that, we calculate a precision as the division of the 1 by the number of steps. We set the length to be equal to 0 initially, and then what we do is we perform rough approximation with each of those steps. So what we do is each time we get the point and the next point, right? So we take the current parameter and then the next parameter that we would be looking at, right? And we just subtract them, then we calculate the magnitude. So what this does is it's like, let's see, I think it's called Archimedes formula for calculate, or Archimedes circumference approximation, I believe. I don't know if there's an actual name for this type of technique, but basically, yeah, okay, so this is kind of the same. You can see here we have, a circle, and we're basically going through all of this and checking each of these individual sections, right, as its own. So we go from this point to this point, and we check the length between these 2 points that we've selected, and then we go to these 2 points and we do the same, right, etc., etc. In this case, I think we do, inside and outside, and then we average them or something, but either way, the point is that what this does is it gives us a fairly good estimate of the length just by taking a bunch of small, linear approximations. And then what we do here is we get a lengthwise position. So what this means is we have a desired parameter, I believe. And we basically want to get the position that corresponds to, or the parameter that corresponds to the position that we want. We give a precision of the parameter. So this is important because, again, we're approximating over small intervals. We have to decide how small we want those intervals to be. And there are a lot of ways in which you could improve this, I think, which is something I really should mention right now and stress. The biggest of which would be subdividing into separate pieces of track, and maybe normalizing precision with respect to the length of each piece of track, right? So instead of just saying, each piece of track gets the same amount of precision, because, for example, if you have a track that's 1 unit long and one that's 1,000 units long, the one will be at 1,000 world units more precise, since the parameter is the same precision on an absolute basis. So yeah, that's just one quick thing. And then, baking these. So pre-computing, removing the real-time component. I just thought real-time looked kind of cool, and also it was kind of lower effort, I think. But yeah, so we basically calculate t as get lengthwise parameter, right? So lengthwise position, lengthwise parameter is then called, and then we return the spline position of this parameter. And so get lengthwise parameter, a little bit more important. And the way that this works is, instead of getting the position based on an actual length, what we do is we get the length based on we get the parameter for a length, right? So basically that's why we're just taking that parameter that we've obtained here and we're plugging it into the position function. And so what this does is it looks, right, we start with found as false, and we go through with our parameter initially being 0, our length being 0, and we continue until we find it or until we get to the end of the track. So the way this works is each time, again, increment the length by the estimated length traveled over this parameter. If the length is greater than the desired length, right, and we don't need to put equals because these are floats and that won't even be a thing anyways, then we set found to be true, we'll break out of the loop and we'll return the parameter. Otherwise, we'll add on 1 unit of precision, and we've already adjusted the length, so we'll just continue until we get there. And last thing is to get the track type. Again, very simple stuff there. So yeah, now this is the last part we need to go over, which is the physics. This is frictionless, I should mention. I could have done this with friction, but I am lazy, so I did not. But the way in which you would do friction is kind of complex, or yeah, a little bit complicated. Like, so you might think that friction should just be, and I actually got this pulled up just so I could show this kind of explanation of the downward component and how we calculate how fast we're accelerating. But this downward, or this component into the slope, right, which is the normal force, is mg cosine theta. In this case, we can disregard m and just calculate g cosine theta as our acceleration component with respect to world gravity. And basically my thought was that we don't actually want to apply just a downward force, right? If you were to apply physics to this model, there would be a few components. The first component, right, is obviously the downward physics, but then you have to consider that roller coasters and, you know, objects moving along curves of any kind have a centripetal acceleration that also contributes to their friction, right? So you have centripetal acceleration, and that contributes to the g-forces that are being experienced by the car, and that contributes in the vertical direction, meaning in this case the direction, so like if you're riding on a ride, you can be at an angle, whichever angle would have the passengers facing upward, and therefore the wheels facing upward, and the axles normal to the, or in normal to the axles basically. That would be the upward direction, we'll call it. Right, so that's the normal vector to a plane. That upward direction has its own component of force applied on it. That's one coefficient of friction. And then the other coefficient of friction would be the centripetal acceleration at the other angle plus the gravity at that angle along the side of the car. So if you imagine this is the car here traveling along the track towards us, you know, you have, if you're curving in this way, right, and you're curving up, you have this downward component and you have this sideways component from the gravity and from the turn. So those are things to think about in terms of how friction is applied here. But disregarding that, we're going to go back in here. Again, we've covered the meat of this, but what we now need to do is just handle some basic physics. So first things first, we want to calculate the length of the spline, as mentioned before. This is just going to be used to reset the car so that we don't just keep going and end up, you know, wrapping around to, like, you know, position of 10,000 or something. Instead, we just reset it to 0 for simplicity's sake. Okay, and then here we set the current parameter, right? So we're going to get the lengthwise parameter for the current position, right? So P is the position. And here what we're going to do is we're going to get the spline position for T. We're going to get the delta for T. We're going to get the transform.forward of the car, or of the ball, right, to be equal to delta. Pointing it in that direction just means that if you attach a camera, right, so like I have here, you can see it snaps kind of nicely. And this would be, well, this wouldn't be ideal, I should say, if you were attempting to use this in like an actual realistic simulator type setting, because the roller coaster is usually not facing exactly upwards, especially in turns, as you'll see in a second as we come around this turn here. But yeah, I thought it was a nice effect. You can see it looks kind of cool, but it's a little bit snappy because of, again, what I mentioned with the angles and stuff like that, and a lack of interpolation between segments. But yeah, that's just kind of what I did. It was a bit bare bones, but whatever. So yeah, if delta has a positive magnitude, right, so if delta isn't 0, and I think that this is only used here because if the magnitude of delta is 0, this normalization step will cause a divide by 0 error. You could fix this by just adding a ternary statement, but I put it in an if statement for some reason. But yeah, basically we add whatever the speed is, so that's why I pulled up this formula. Again, we've got g cosine theta, right? So in this case, first off, g, right, gravity, the y component of gravity, that is, and time.fixed delta time. Time.fixed delta time, again, being the way in which we can normalize with respect to our frame rate the acceleration. And then this part here is kind of unintuitive at first, but you should realize that even though we're looking for mg sine, or g sine theta, right? We've already taken care of g here. This actually functions as sine theta because sine theta is actually opposite over adjacent, and in this, or opposite over hypotenuse, and in this case the hypotenuse is the magnitude of the derivative of the spline, and delta dot y is the opposite component of the spline, right? So that's the vertical component, and the other component is the outward component. Little bit tricky, I think, just if you're not really familiar with that kind of math. But again, pretty simple in the end. Not really sure what else to say about that particular aspect of it. It is kind of weird, I guess, on a conceptual level since it's 3D, but again, the math should check out. And yeah, the last step here, last major step, aside from, again, wrapping the car around to 0 if we get past that, is we have to add to the position each time. We do that by just adding the speed times the frame rate normalization of time.fixed delta time, since this is a physics process, even though it's technically not physics by Unity standards, just kind of our math stuff, but we're doing this as physics math, so I think that that's appropriate. And a switch statement, and this switch statement just basically we've done some stuff with the speed, but we set the speed manually in some cases. So here, if it's a lift, we clamp the speed between math.infinity and 2f. What this does is basically, like on a real roller coaster, the car can be going faster than the chain, and if the car, due to gravity and friction slows down enough that it's slower than the chain or falling backwards, it catches on the chain and therefore reaches a minimum speed. So we clamp it like that, and as gravity pulls it back, eventually it'll hit the minimum value and just start moving like that. Which is how we get that nice, chain property that you can see right here. You can see it sort of slows down, but it doesn't stop. It just clamps into a minimum. And the last bit is the braking section of the track. So brakes, the way it works is we just set some value, right? You could set this to be any coefficient. I chose 1.5 f, and basically we just adjust the speed of the car manually according to a combination of the existing speed and the time.fixed delta time. Now, you could debate this. I think there is something to be said about the fact that technically this should realistically be, first off, 0 if the speed is 0, right? And, not actually a multiple of speed. So like the way brakes work is usually just you're applying extra friction to the side. So what you could do maybe if you wanted to be kind of more precise about this is say speed is equal to 0, right? And say, speed, right, if it's 0, you're just going to make it 0, right? Otherwise, you'll say, right, speed divided by math.abs, mathf, I guess, divided by speed, right? And what this will do is, we're not actually going to apply this right now because we would have to come up with a new coefficient. But what this will do is it'll just make it so that speed is not a variable here. Instead, we'll just be using the absolute value of the speed and the speed. If it's 0, right, we don't want to apply friction. If it's greater than 0, We want to apply friction in the negative direction. If it's less than 0, we want to apply friction in the positive direction. So that would account for all of that if you wanted to do that. Otherwise, we do nothing if the track is normal, or otherwise, right? We can write anything in that slot. And yeah, that's how this all works. That was kind of a really long-winded explanation. Obviously, one of the longer videos I've uploaded recently, probably, well, I haven't uploaded recently, but one of the longer videos I've uploaded on my channel, I would say. If you got through it all, make sure to leave a like, comment, subscribe. If you enjoy this kind of content, let me know what kinds of things you want to do. Thinking about, doing some stuff on circuitry and, web development and stuff like that. Not necessarily as much Unity-focused stuff in the future. So let me know what you think about that. And yeah, stay tuned for some more videos in the future. Bye.